Okay, hi everyone. My name is Kayla Blalack. I'm a rising senior undergraduate student at the University of Virginia. And I worked on this Origami Robocasting project with PhD student Lilly under the guidance of Lilly Balderson under the guidance of Professor Towson. So we'll start with just a little bit of the industry applications of this project. We'll look at why robocasting specifically for the origami application. And then we'll talk a little bit about the origins of this origami robocasting, the precursors to the method. Then we'll look at the objectives and challenges for this project and our specific ink formulation, and moving on to the printing process, what we've been able to achieve, and the meat of our quantitative results is going to be the comparison between two different polymer binders in the ink. Then we'll conclude and see some more areas to explore. The underlying application of this work is any industry that requires complex ceramic geometries, such as high temperature aerospace components, there's a nozzle there, complex tissue and bone scaffolds, or catalyst supports that require precise geometries and high surface area. So there's this need for structurally and compositionally graded components, which is where robocasting can be very useful. And the current best manufacturing methods for these are mold casting, which can't create hollow components, and it also isn't very suited for that rapid prototyping or higher density manufacturing. So why robocasting? It's super cost efficient, it's really accessible, it doesn't require the same tooling that a mold would, and it can create those functionally and compositionally graded structures with the layers. And the use of the origami flexible foldable ink expands even further those geometric possibilities in the slurry extrusion. The origins of the method were right on. They used a titanium-based ink, which is an ancestor of our formulation, and created many of these small-scale parts like the cube and the crane that you can see here. And the expansion of this into the field of ceramic parts generally focused on polymer-derived ceramics, which need fillers to reduce the cracks and increase the density, and they're also very limited in the material scope. They're generally only silicon-based components. They also use a pyrolysis process that generally downgrades their mechanical performance. So here on the right, you can also see that the PDC that they used is limited in its shape memory and needed a wire in order to support it during the sintering process. For our projects, the objectives on the macro scale increase geometric possibilities for this method. I used Balderson's novel ink formulation and applied it to origami robocasting, and then I compared two different polymer binders, a polystyrene and a polyethylene oxide, at different volume percents. Then I just wanted to demonstrate the geometric possibilities while working with the challenges of fine-tuning that ink formulation, getting it perfect for printing and manipulation, and also standardizing these processing and printing steps to be able to scale it up for identical prints. Finally, we wanted to optimize the properties of the finished components, properties like density. So the ink formulation. The two main components are the ceramic powder and the polymer binder. We experimented with a base powder. We started with alumina because it's super common in literature and it's a great stepping off point. And we chose the ratios of 80, 70, 75, and 70 volume percent in order to get the maximum density possible in our sintered prints without limiting the performance of the ink. As you increase the volume percentage of the alumina powder, the ink becomes crumblier and it's harder to extrude from the nozzle. Then the polymer binders, as mentioned before, polystyrene or polyethylene oxide, they act like the clay or putty to hold together the ink. They create the ink's shear thinning properties. They have high yield stress, which makes it act more like a solid when printing, and it has a higher storage module. They also provide more of that shape support when sintering. And the trisolvent system, the third component of the ink, has dichloromethane to volatilize under shear stress and allow that ink to set as it prints, the EGBE to make the ink self-healing and adhere the layers, and the DBP to enable that folding behavior. Another great component of the same formulation is the ability to use multiple materials. As shown in the black here is silicon carbide in addition to the aluminum. Because the ink base is inert, it can be combined with any ceramic powder. Other notable features are its sustainability. This ink is recyclable, so any unused ink or failed prints can be redissolved with dichloromethane and reused for future prints. Now getting into the printing process, as we went about printing and optimizing the machine settings, we arrived at these in the table here, and our conclusions in general were that the PEO binder is thicker and greater viscosity, which led to it requiring slower printing speeds. However, the post-forming time is one of the most important capabilities, and the polystyrene becomes much more brittle more quickly, so that PEO is much better for shaping post-print. We use thermogravimetric analysis to design our sintering profile, and by observing when the polymer burnout occurs, we designed this burnout profile. First step is the polymer burnout at 600 degrees Celsius. It removes all of the polymer and it leaves behind the carbon structure that supports the form during sintering. The second at 1625 is densification, and then we conclude with controlled cooling. After the dissolution, processing, syringe loading, and printing, we get into the origami process, which starts with that preformed flat shape. Then we remove it from bed after letting it sit to partially set, and finally we shape it with the aid of hands or other sort of shape molds. This ink is self-healing, which means you can press it together after print to join with itself, but depending on the set time, you may add additional ink in order to completely join those boundaries. And the green body doesn't need aids to maintain its shape either before or after sintering. So once you've shaped it, it holds. Some of the shape capabilities that we were able to demonstrate: number one, folding. We created these shape nets, which can lead to hollow parts. And we demonstrated that with this triangular prism, as well as this lattice cube, which is another example on an even larger scale, that 5-centimeter cube. We're also able to twist and roll the parts, such as these Mobius strips. And we can combine multiple origami techniques to create complex geometries, such as these butterflies. One interesting note about this process is that we observed that you need to orient the parts while sintering with the center of mass closest to the bottom of the crucible. So in this case, the butterfly on the right, which was our best surviving butterfly in the sintering process, was oriented on its back, whereas as opposed to putting the wings on the bottom. So now let's get into more of a data-driven comparison of the polymer binder performances. As you can see, as the polymer loading increases, the density of the final part decreases and the shrinkage increases. Polystyrene had the highest density at 95% aluminum, but PEO had a highest density at 89%. The shrinkage for both binders had a very similar trend, but there was slightly smaller shrinkage from the polystyrene. And on a more microstructure level, from the layer interface, we observed that the polystyrene binder is essentially indistinguishable with the layer boundaries as complete diffusion in the sintered part. PEO, being the bigger polymer, keeps solvents from diffusing through the layers effectively, so it creates more of those bubbles on the layer boundaries. Those fusing issues occur more in bulk structures, which is why we recommended polystyrene more for bulk parts. However, we're doing additional work to mitigate those fusing issues in the PEO with the addition of a plasticizer. And more on microstructure, as you can see, they're very similar, and the only big difference between the two is that pore formation mentioned at the layer interface. For XRD, there's essentially no difference between the powder and the sintered prints with either polymer, which means it's staying in the alpha phase throughout, nothing changes or recrystallizes, making this method very effective for functional materials and catalysis applications. So to recap, for the differences between our polystyrene and polyethylene oxide, polystyrene is much more preferable for bulk parts and high density parts, but the PEO is preferable for shaping parts, overhangs, and shape retention when sintering, which are some crucial elements of this origami method. PEO burns out into that carbon structure. With more carbon, it supports the shape more during sintering, and PEO has a higher storage modulus, which is better able to create those stunts and overhangs. We're experimenting with the addition of PEG to PEO in order to reduce the microstructure and other issues that the polystyrene is stronger in. So in conclusion, Our sintered alumina prints exhibited high density and moderate shrinkage without any issues such as cracking experienced by previous literature, and it maintained those manipulated green body shapes, which opens lots of potential for more advanced geometries in the field of ceramic robocasting. In the future, we're looking at further standardizing those ink and printing processes, expanding the compatible materials, testing those green bodies and the sintered bodies for mechanical properties, and finally, looking at process scaling for larger components and faster printing of components.
You got time for questions? You got your hand up, Mr. Perry.
I thought that was a very interesting presentation. I like it.
Thank you.
I'm wondering, so you are basically printing this 2D shape and some you change to 3D.
Yes.
And that's what you're done. So how can you hold it shape when after you change to 3D?
Right, so you're folding it either with your hands or a mold,
Yeah.
and the volatilization of the dichloromethane enables the ink to set. So it hardens, where initially it was more of a liquid coming out of the extrusion, and then it becomes a solid.
Okay.
Yeah.
Could you tell us how this, you had a chemical that enables self-healing? How that works and enables it to self-heal?
So the DBP, the dibutylphthalate, it's a plasticizer, and the EGB has a low volatility, which means that between those layers, it keeps it from setting too quickly. So you have the dichloromethane, which allows it to set in order to maintain that shape. But the EGBE tempers it a bit and allows the layer boundaries to fuse into each other before fully setting.
Thank you.
Yeah.
Back
I couldn't quite read from here. What was the shrinkage
Oh,
that you saw?
So at the lowest polymer volume percent, it was around 17% for the polystyrene and around 23% for the
Have you seen
PCL.
any cracking?
No.
No.
Yeah, and that's partially due to that EGBE, which solidifies the shape. Yeah.
1 second.
I guess my first question is to ask, so you use this polymer 1% up to 30%, correct?
Yes.
Okay. Another question is this, when you show this lattice cube, so how can you change it from 2D to lattice cube?
Oh, you print, I actually have a supplementary slide on this a little bit. So this is an example of a failed print, but you can see the shape net there.
Okay.
You print the flat version of a 3D, and then you fold the sides
All
up.
right, okay. Thank you.
Yes.
Were you controlling the humidity in the environment when you were printing?
No.
Okay, so then okay.
Yes.
So you mentioned going for the center of the mass on the bottom of the crucible during sintering. Is that because you see some sort of like structural collapse during the sintering process as you keep the material up?
Yeah, so one of our challenges that we were working with when creating these parts that survive sintering is to balance the components in the ink recipe. So when you have a thinner ink, especially an under-processed ink, it's more likely to collapse. And when you haven't let the ink set for too long after printing and forming before sintering, it tends to have more of that deformation. So we were balancing multiple components of the process, and one of the ways that we found to mitigate, if we had forgotten to let it sit for too long or if we had under-processed the ink, was to sinter it with the center of mass lower.
I have a related question, I guess. So I'm assuming that it's gravity pulling down that's causing it to sag, and that's what the problem is, and that's what you're trying to mitigate.
Yeah.
Have you looked at supporting the sample with some kind of external mold so that it wouldn't collapse during that drying or sintering process?
Yeah, absolutely. This is what a lot of our precursors did. They sintered it with just a mold, using the ink in the mold. One of the great applications about this ink is that it has a little bit of that ability to break free from the mold dependence. However, that being said, you can see on this slide too, the titanium foil, platinum foil can be used to support the part without fusing during sintering, so you could easily
You
make
can use
a
a flexible,
structure out
yeah,
of
make
foil.
it flexible,
Yeah.
sort of temporary.
Sorry, I got one more question.
Mhm.
Essentially, my understanding is Robocasting is using aqueous-based with a very small percentage of binder, but your binder is up to 30%. So can you call that Robocasting?
I mean, it's getting into semantics, really.
Alright.
It's an extrusion of a slurry-based ceramic egg. Yeah.
There's a few more questions, you wanna keep going?
Sure.
All right,
I love
we've got time, but yeah, don't wanna torture you either.
Two
Yes.
quick questions. What happens to the carbon in the burnout? What happens to the carbon from the center?
So the carbon during sintering creates that lattice structure, which enables it to maintain the shape without that external support. If your question is, what happens to the carbon, is it just an alumina and carbon structure after sintering? It does eventually burn out.
The carbon does burn out.
Carbon monoxide or carbon dioxide or something. You back? Yep.
Yeah, there was a slide where you highlighted the relative, setting time. How long does it take to set?
For the polystyrene, about 5 minutes to set before it cracks if you try to bend it. For the PEO, about 20 minutes, as you can see. But we've seen, and to your comment about the moisture content in the room, we've seen some of the polystyrene prints be flexible even a day after.
Very good. All right, one last question. Yes, no, go ahead. We got time.
This is regarding what he said. I guess, have you made any attempts to do biological characterization as the material cures or dries or sinters? And like watching the fall and see sort of what this changes?
No, but that would absolutely be a great future application.
Very good. Thank you very much, and thank you for
Thank you.
entertaining some of the questions.